All right, Algebra 1, Lesson 26, Recursive Challenge Problem, the Double and Add 5 game. This sounds challenging. So recursive means something that we'll get to, but we're going to sort of talk through a game during this lesson. First of all, I added a little bit of notes in here. I'm not sure if they are in your problem set or not, or you're in your classwork. The double and add 5 game is loosely related to the Collatz conjecture, which is an unsolved conjecture in mathematics named after Lothar Collatz, who first proposed the problem in 1937, and it is still unsolved. Crazy. The conjecture includes a recurrence relation, triple, and add 1 as part of the problem statement. It's a worthwhile activity for you to read about the conjecture online. I would be willing to put some bonus points to somebody that wanted to write a short essay about this whole conjecture problem, because I've not done any research. So you can learn something and I can learn something. So let's look at this. First of all, this activity really describes the process so that you can be given the problem statement. We're going to create an interesting sequence by doubling and adding 5. So we're going to work through this table, and we have a starting number. So we're going to have that starting number. We're going to double it and then add 5. And then that result goes back into round 2, where we will double it and add 5. The result of that gets entered into round, I didn't do this one, sorry. 7 times 2 plus 5 equals 19. That goes into round 3. So 19 times 2 plus 5, that is 38. Plus 5 is 43. Double that is 86, plus 5 is 91. Double that is 182, plus 5 is 187. So we just filled out our table. We had our starting number, and then each round gave us a new result that we would plug into the next starting number, correct? All right, let's move on. If you guys could please complete the tables below for the given starting number. Double and then add 5. Double and add 5. Go ahead and do that on your own. I'm going to give you the answers in a minute, but you guys can do this one. All right, there we go. I hope you did this one correctly. It's not real rocket science, and we all have some cool calculators to help us. Moving on. Mathematical modeling exercise, exercise 2. Given a starting number, double it and add 5 to get the result of round 1. Double the result of round 1 and add 5, and so on. The goal of the game is to find the smallest starting whole number that produces a result of 100 or greater in 3 rounds or fewer. All right, this is our problem. So what are we going to do? You guys want to test a few things. What happens if we start with 10, where round 1 we would have 10. 10 times 2 plus 5 is 25. That's round 2. 25 times 2 is 50 plus 5. So we have round 3. 55 times 2 is 110 plus 5 would be 115. Does that work? Looks like it. Will all numbers greater than 10 work? I think so. Can you find a number smaller than 10 that also works? If you start with 8, my first round, I'm going to do this in my head, gives us 21. We go 21, we get 47. We start with 47, and we get 99. So no, the number 8 as a starting point does not work. How about the number 9? Double that, plus 5 is 23. Start with 23. Double that, plus 5 is 51. Start with 51, and we got it. Double that, plus 5 is 107. Yes. So 9 works. Is it the smallest? Yes. 9 is in fact the smallest whole number that we can get. That gives us a solution greater than 100 in 3 rounds, right? 8 was too small, 10 was pretty big, 9 was just right. Cool? All right. Let's see if we can take this any further. Is there another method for finding the answer? For example, could you work the problem backwards? If we had 100 as our solution, 2 times a number plus 5, would this work? Well, let's add or subtract 5 from both sides. I've got 2n equals 95. Divide both sides by 2, and I get 47.5. So this has to be reached in 2 tries, 2 rounds. Right? So we can do that again. 47.5, subtract 5, which is what I did, and then divide by 2. That gives me a solution of 21.25. This has to be reached in the first round. So what first number do I have to start with? Let's do it again. 21.25, subtract 5, divide by 2. That gives me an answer of 8.125. Or the whole number. If we round down, we're too small, so we have to round up to 9 as our answer. All right? Okay. The next goal is to solve the problem, but find the smallest number that results in 1,000 in 3 rounds or fewer. 1,000. So we want to reach 1,000 in 3 rounds or fewer. What do you think? How are we going to do it? Do you want to guess and check? I don't really like guessing and checking, so that's really not my favorite thing to do. I don't know if it's your favorite thing to do, but not my favorite thing to do. It's not as easy as 100, so guess and checking will take you a while. And I know you guys like the easiest way to do things. Like that's what makes you guys tick, right? Easiest way to do anything. So let's formulate an equation. How do we formulate an equation? Formulate an equation. This is when mathematicians, they create and describe recursive sequences. It's a new vocabulary word for you guys. Recursive sequences. We're going to see this again as we go on in Algebra 1. This is our first instance, though. So mathematicians create and describe recursive sequences. And how they do that, we come up with A1 is the result of round 1. Round 2, the result is going to be called A2. Round 3, your result, your answer, is going to be called A sub 3. That's the name of it. It's sort of its nickname, where Joseph has a nickname of Joe. Round 3 answer has a nickname of A3. So if these are the results of the rounds, we can label them all as so. So round 4 would be A sub 4, round 5 would be A sub 5, etc., etc. What do we do with the beginning? The beginning input, what do we label it? The first input, we're going to label it A sub 0. It's the first thing that we plug in. So for one of the examples, we had A sub 0 equals 5. So if we double it and add 5, A1 is going to be 5 doubled is 10 plus 5 is 15. So we come back over here, we say A1 equals 15. We double that and we get 30. So A2, the result of round 2, would be 35. We start out with A2, double that, which is 70, plus 5, which is 75, etc. So we have our starting number and our solution. What's cool is in between these two things we have an equation. Our equation would be a sub 0 times 2 plus 5 equals a sub 1. Okay, I just wrote that all down for you. Again, I would love it if you would extend this table to a sub 3, a sub 4, and then see if you can come up with something that is a sub I, and then a sub I plus 1. I'm sort of pushing you a little bit here, but I know you can do it. Okay, we always refer to the one previous, and then we would add one to my sub number for the next one. All right, so see if you can come up with these, okay? I'm going to push pause. You can do it. All right, there you go. Jot that down. It's going to be grand. I would like to point out a few very important pieces about that last slide. Our original input is 5, and every input past that is going to be 2 times the previous plus 5. That's sort of our equation. We always know I is going to be greater than or equal to 0. Okay, that's our sub, right? This right here is called, if I could spell, recursive equation. An equation that works in a way that we plug in the previous number, the previous answer, to get a new answer. Okay, that's what a recursive equation is. We're plugging in the previous answer to get a new answer. And then you plug that in to get a new answer. They plug that in to get a new answer. It's like a chain. Never ends, right? All right, let's try another exercise. So using a generic value, a sub 0, and the recurrence relation, a sub I plus 1 equals 2 times a sub I plus 5 for I is greater than or equal to 0. Find a formula for A1, A2, A3, A4 in terms of a sub 0. Okay, we've sort of done this. I bet you can do it. A1 is going to be 2 times a plus 0 plus 5. A2 is going to be 2 times a sub 1 plus 5, which is going to be 2. Look, we can replace that. 2a sub 0 plus 5 plus 5. All we did is we substituted, instead of a sub 1, we put in this because this equals a sub 1. Substitution. Excuse me. I can simplify this to 4 a sub 0 plus 10 plus 5 equals 4 a sub 0 plus 15. Next one, a sub 3 equals 2 times a sub 2 plus 5. Ooh. Instead of a sub 2, we can substitute this. Getting a little fun. 2 times 4 a sub 0 plus 15 plus 5. Just did a little substitution, right? So that gives me 8 a sub 0 plus 30 plus 5, which is 8 a sub 0 plus 35. My answer. On the next slide, I'm going to do a sub 4, so make sure you have everything written down, okay? A sub 4 is going to be 2 times a sub 3 plus 5, where we know a sub 3 from the previous slide equals 8 looking at the wrong thing. 8a sub 0 plus 35. So we're going to substitute. We're going to say 2 times a sub 3 plus 5. Distribute. 16a sub 0 plus 70 plus 5, which is 16a sub 0 plus 75. Phew, that was fun. That really was the end of the lesson, too. I've got some vocabulary in the next page that I would love it if you'd look at, and we're going to work through a few of these things in your problem set. Cool? Awesome. Good job. Here is your vocabulary, though. Sequence. We talked about a recursive sequence. Ordered list of elements. What else? Recursive sequence. An example is defined by specifying values of one or more initial terms, and then having the property that the remaining terms satisfy the recurring relationship. So value of a term based upon an algebraic expression. Previous terms are very important. Okay, that's how we'll keep plugging things in. But that's it. Okay, we will work through the problem set tomorrow. Good job.